But yeah, let us try to give you a very brief overview as much as I can yeah, about this. And so that is what we are doing right now. Right. So as I said, DNA, mRNA, protein, it's easy enough. Can you all see the board? Can you all see
Yes,
the
sir.
board? Yeah.
Yes, sir.
Yes, sir.
So, yeah. So let us start. Unless you have questions. I mean, this is what I'm trying to tell you, that, what I'm trying to tell you really is that I am oversimplifying all the time. And there is a need for oversimplification, because we get into depth in one subject, we will be stuck there forever. And that is a necessary requirement of the fact that courses have been divided into separate sections. And unfortunately, there are huge linkages between courses, subjects. They eat into each other. So if I want to talk about enzyme overproduction, I actually need to talk about bioprocess design as well. I do not know. You have done a course on bioprocess optimization with Professor Narang or somebody? Hello?
Yes, sir.
Yes. So you have
Yes, sir.
you know about fed batch and designing fed batch cultures for protein production. You know about DO, you know about KLA, you know about all those things? You have heard?
Yes, sir.
Yeah, okay. In which case, I will, in one class, very briefly touch upon the bioprocess issues in protein production. And I will borrow those concepts, and I hope that you remember those concepts. It is also important for me to demonstrate to you the interlinkages of these forces. So right now, of course, let us continue where we were, and we were talking about promoters. Can all of you see the board? Yeah. And essentially what I was saying is that the promoter is essentially doing this job, DNA to mRNA. And the whole idea is to have an on-off promoter as much as possible, so that we can ensure that this process is off in the first phase of growth phase, thereby ensuring plasmid stability. Because growth phase, your alpha values will be close to 1 or approximately 1, because mu minus is approximately equal to mu plus. Mu plus will fall only when DNA is getting transcribed to protein, and so then mu minus will become much larger than this, and you have all kinds of instability. So the production phase is where mu plus is going to fall. So really we want to make a lot of mRNA. So when it's normally off, and then at some point I switch it on. When it is on, it makes a lot of mRNA, and the fold increase between on and off, because these are not electronic switches, whether it is 10-fold or whether it is 100-fold or whether it is 1,000-fold increase between on and off is what determines the degree by which it is tightly regulated. And that is one problem. So tight regulation is one problem, and as I said, titratability is also an issue. Is it titratable in the sense that if I increase the amount of inducer that I add, will the rate become higher? The reason for titratability is the following. We tend to assume that this is the rate limiting step, but it is not, especially when expression levels are high. So the assumption of rate limiting step is questionable, because further steps downstream might be rate limiting. And as I said, one of the proofs of this is that your transcription rate may go up 10-fold. Let us say transcription rate has gone up 10-fold. But really, the mRNA concentration, remember, mRNA is being made, it is also getting degraded. And this is an important concept that I want to sort of emphasize. mRNA steady state concentration inside the cell, the desired mRNA, which is for your protein, because there are many mRNAs, the steady state concentration inside the cell may only go up 4-fold. Let us say, I'm just putting some numbers for you to sort of follow the argument. Now, the reason it has got 4-fold, because even though the rate of, is because, of course, more mRNA is being translated, but also mRNA is undergoing degradation. So what really happens is that when you try to make a lot of mRNA, assuming that it will all go into the protein that I'm talking about, what really actually the cell does is simply starts degrading the mRNA. So you are unnecessarily making a 1,000-fold increase and you think you have a very good promoter and your life is going to be easy, you're going to get a lot of protein. You are not, because the mRNA degradation rate also tends to increase. And this is a very conceptual and an interesting problem. And we used to ask this for biology students because they don't know arithmetic very well, unlike you guys, is that, you just, for example, and this is a side business, suppose you try to calculate what is the rate of ATP production inside the cell and ask them how much ATP is produced in, say, 10 minutes. You can look at the electron transport chain, you can do the biochemistry, and you can do the rates. And then you tell them, okay, what is the weight of a cell? And what is the ATP you have produced? And it turns out that you have produced 100% of the cell volume in 10 minutes. So the amount of ATP is equal to the weight of the cell. Of course, that is not true, because what really is happening is not that the ATP, steady state ATP levels inside the cell are 0.1% or 0.2% of the total cell weight, of course, what I mean. But it is not 100% because there is a turnover. So whenever you have, and people tend to forget that whenever you have A going to B going to C, which is what is happening with most molecules are somewhere as B, whether it is mRNA or whether it is, this is a general principle, that they are also being made and they are also being consumed. A very simple example, for example, A going to B going to C, a central molecule is, say, pyruvate. Now the rate of pyruvate formation is extremely high, but so is the rate of pyruvate consumption. And the steady state concentration of pyruvate inside the cell changes little. The steady state concentration changes little and often is a very poor measure. Is a very poor measure of the rates at which pyruvates are being formed and the pyruvate is being used. And that is the biggest problem with metabolic engineering, because what you do end up is measuring steady state concentrations of various metabolites inside the cell, and that is what we keep on doing with mRNA and proteins as well. But it gives us very little idea of the fluxes, because what you're not interested in the steady state concentration. You are interested in the flux, the input and the output. So just like a CSTR, you do not know, the volume is constant, but whether the flow rate is 0.5D or 1D or 5, whether dilution rate is 0.5 or 5 or 50 or 0.05, you don't know. The volume is always a constant because, input is equal to output. So steady state concentrations tend to change very, very slightly. From 0.1% may go up to 0.2%. This doubling may reflect actually a flux which has gone up 10-fold or 5-fold. So these are not easily related. About metabolites, at least you can say something. About proteins, actually you can say nothing. Because, sorry, again, this is stuck. Can you see the board? And can you hear me?
Yes, sir.
Yeah. I mean, is it that I talk too fast? आप लोगों को सुनाई देता है? I mean, once while teaching abroad, people told me that Indians tend to talk too fast. But I said, well, only Indians can understand speed talk. And so I think that you people don't face such problems, right? You can follow what I'm saying? I have this tendency to speak fast.
Yes, sir. Yes.
Okay, thank you. So tell me wherever you don't understand, ask me. So the conceptual problem that I'm trying to point out is that, and which is true for all over systems, is that steady state concentrations and fluxes are not easy to correlate. Steady state concentration and fluxes are not easy to correlate. The flux is input and output, and they usually tend to match, and almost all cells by definition will reach steady state, or what I should call quasi-steady state or pseudo-steady state, in terms of concentrations of various metabolites and proteins. But they don't change significantly with time. And I will come to this concept about time and window of observation later on. And have you heard of, sorry, I should not jump and here and there, but have you heard of a concept called relaxation time? Sorry?
Can you define flux here?
Yeah, flux is rates. Flux is rates of input and rates of output. A flux is the pathway flux, for example, A to B to C, is that at steady state, what is the rate at which A is forming B, B is forming C? Is it 10 millimoles per second? In per cell, of course. millimoles per second or 1 millimole per second per unit biomass, of course. Everything, all calculations by definition, because they are per unit cell, are therefore per unit biomass. I mean, you cannot otherwise talk talk meaningfully about anything, right? Everything is per unit cell. That is why whenever we talk of growth rate, whenever we talk of product formation rate, whenever we talk of everything, we use the word specific. I hope you are familiar with the word. We never talk of growth rate of cells. I mean, growth rate of cells makes no sense because 10 cells will become 20 is the same growth rate as 1,000 cells becoming 2,000. But whether 10 cells are produced, so when you have 10 cells and they become 20, and whether you have 1,000 cells becoming 2,000, so obviously the rate here is much higher. dS by dt is much higher per unit time. But this is growth rate. But the specific growth rate is 1 upon x dS by dt. That is equal for both these things. Similarly, we never talk of product formation rate. We talk about 1 by x dx by dt, or a specific product formation rate, which is QP. These are by definition, right? These are by definition. These are defined as. Or when we talk about substrate uptake, we talk about 1 upon x ds by dt, which is by definition QS. You have heard of these terms in bioprocess. Now,
Yes, sir,
these
yes.
mu, QP, QS are related to cellular health. These are functions of cellular health or cellular physiology. So these are all functions of cellular health. But these are, so all rates have to be always specific. The word specific really means per unit biomass. Specific growth rate, specific product formation rate, okay, specific substrate consumption rate, specific product formation rate, specific substrate consumption rate, substrate consumption. Oh God, this is really irritating. So can you see me and hear me? Yeah. Specific substrate,
Yes, sir, yes.
I'm writing specific substrate consumption rate, and it goes on and on. I mean, and for example, it is also a specific oxygen consumption rate. Okay. It is OUR is always oxygen uptake rate or oxygen consumption rate. Okay, and then you match it with various KLA devices and so on and so forth, or specific carbon dioxide production rate. And all these are correlated with the stoichiometry and the rates. So they are the ratios of these things: growth rate, product formation, substrate consumption, oxygen consumption, carbon dioxide production, are related to each other by complex stoichiometry, which is what would have been taught to you. And the rates are so that is the ratios between these flow rates, these fluxes, the flux of oxygen uptake, the flux of carbon dioxide production, the flux of, and you would not have done intracellular modeling. I know we don't teach you intracellular modeling, but you can well imagine that within the cell, ATP production or pyruvate production also per unit biomass, there is a certain rate. But remember that pyruvate may be produced and consumed at a certain rate, ATP may be produced and consumed at a certain rate, but the steady state concentrations inside the cell do not change much. So the rates are not necessarily correlated very well with the steady state concentration. Am I making sense?
Yes, sir, yes.
Okay, so the point that I'm trying to make is that protein production is even worse, because proteins may be building up, but what is the amount of protein produced is also dependent on how much is getting degraded, and there is absolutely zero idea. Mammalian cells have a very complex system. Can you tell me what is the system of protein degradation in mammalian cells? What is they have a very, very interesting and complex system of protein degradation, where proteins are targeted for degradation. Have you heard of that term? Anybody? It's called ubiquitination. Have you heard? No, you have not done cell biology.
No, sir.
You have done. You have forgotten. Anyway, so but E. coli and small bacteria do not have complex systems, and therefore the bacteria, which protein exists for how long, is dependent on how much it is formed and how much it is degraded. But proteins, of course, don't disappear inside the cell, just like plasmids and DNA. Of course, they disappear in the sense that one cell divides into two, the protein concentration will be not at this moment half, because the biomass is exactly the same at the point of division. But when they become equal to this cell, if the protein production doesn't take place, the protein concentration will be half. Okay, but and this is important, we do not know what is the rate of protein degradation. So one of the effects is that the biomass can be thought of as an ever increasing size reactor, and therefore if protein concentration rate formation is slower than the rate of biomass formation, your protein steady state concentration will decline. Right? I mean, let us put it very simply in maths. If you write P is equal to P total product upon total X, then obviously dP by dt will be equal to X square. Come on, let us hear you out. 1 upon X dP by dt minus P dx by dt, right? Okay. Sorry, X dP by dt minus P dx by dt, which is equal to 1 upon X dP by dt minus P upon X into 1 upon X dx by dt. Are all of you following this?
Yes, sir. Yes.
Yes, sir.
This is easy enough. Now, notice that this term here is nothing but QP, right? Rate of product formation per unit biomass. P by X here is nothing but P, small p, the concentration, P here. Right? And 1 by dx by dt is nothing but mu. So we get an equation here, simple enough. With this, these are simple things. I thought you would have definitely done this stuff, so I'm just sort of re-mentioning it again. So we are getting dP by dt, the rate of protein concentration change inside the reactor, inside the cell, is given by Qp minus P into mu. So the rate of change of concentration of protein is dependent on the rate of production of protein minus the concentration of protein into the growth rate of cells. This is effectively the dilution effect. This is effectively the dilution effect that is taking place. That is taking place because of cell growth. Cell is growing, right? So assume in a very simple way where QP and mu are essentially where QP is equal to P upon mu. In which case you can actually have this as 0. So your steady state concentration of P is not changing inside the cell at all, because QP is equal to mu into P into mu. So if the rate of protein production and the rate of biomass production are in the proportion of their concentration inside the cell, really it means that P is increasing, doubling. P is, say, let us say P is in the beginning 10%. Let us say we have 10% proteins, and in 1 hour the cell doubles. There are 2 cells now, and the protein also doubles. 10% becomes 20%. 1 gram becomes 2 grams, and so P remains the same. That is what this equation is telling you. QP is equal to P into mu. So P is 10%. So if this is being produced at 10% of the rate of biomass, then it will always be 10%. Right? Follow this argument? So many times biologists have this funny problem. They load gels. You would have heard of SGS-based gels, and they say that protein concentration is actually declining. It is not declining. Because it is declining because you are taking 1 unit biomass and P is declining. P may be declining, but QP may still be positive. So you may be producing protein, but the rate of protein production is slower than the rate of biomass production. So per cell, the protein will get diluted out. If QP is higher than this, the amount of protein will increase, and if they are equal, then it will remain the same. So please remember that there is also a dilution impact of any protein production. That is something which we are not going to talk about right now. Right now, we are talking about the fact. Let us go back. Sorry. Let us go back. We are talking about the fact that the steady state concentrations of DNA to mRNA is not, the mRNA steady state concentration is not a very easy measure of the fact of how much flux is taking place. And we know for sure that when these fluxes are increased, the mRNA steady state concentration does not increase significantly, not only because mRNA forms more polypeptides, but also because degradation rates go up. So it is not a good idea to sort of simply try and get very strong promoters in line. And that is why the need for titratability. So strong promoters are not always a good idea, which unfortunately biologists think it is. So degradation rates increase. So you need to address downstream steps to ensure that the mRNA which is made is not targeted for degradation, is targeted for production of polypeptide translation. Now, how does that happen? First of all, let us simply look at the fact that do strong promoters always good make large amount of mRNA? And I will answer this question in a minute because I don't want to get into biology, and biologists have this very long. One of the points that, for example, you all know that everything starts with ATG is the start codon, right? But this is the start codon for translation. The transcription can start significantly upstream. And I will not get into, chromosomal architecture, but this is a subject of interest to biologists, and it is, I don't think it will be taught to you. But the ATG start is the translation start, but the transcription start is significantly upstream. And this transcription start can you hear me?
Yes,
Yes.
sir.
So start of transcription is ahead or upstream of, and this start of transcription also is dependent on the sequence. And various sequences tend to give good starts of mRNA, and various sequences give poor starts. So there are designs which talk about when the RNA polymerase binds, we talked about the promoter. So downstream of the promoter, how far away should the transcription start? Hello? No.
Yes, sir.
Just wait. So downstream of the promoter, the transcription start, what should it be composed of? How far from the promoter it should be? All these questions have bothered molecular biologists a lot, especially because it reflects on the efficiency and the rate of transcription. So the sequences, how far away? There is a whole architecture issue which I will not address, but these are addressed by people who design recombinant protein production because they want efficient transcription starts. Not just transcription starts, I will sort of end this by saying that there is a secondary mRNA structure. Have you heard of secondary structure?
Yes, sir.
Yeah, so DNA do not have tertiary structure. I mean, they do have, but let us not get into that. RNA definitely have. So if the mRNA has structures like this, because there is a possibility of forming a loop, or they have structures like this. These are secondary structures which can form in mRNA because of stem loop systems. And these structures, the secondary structures, the more there is energy in the more stable the secondary structure is in terms of not forming, the poorer is the transcription. So you cannot design, always when you design the mRNA, because there is ways of designing it, and I will talk about it in a minute. You should always make sure that your mRNA does not have stable secondary structures which interrupt with the transcription rate. As a matter of fact, you are aware of row-dependent and row-independent transcription stops. And one of the stops of transcription is actually this kind of structure only, right? This kind of structure is there to actually stop transcription. So if you have similar structures in the middle of the transcription, they might also break transcription. So not only is it a problem of slowing down of rates, it is also a problem of quality control, because truncated transcripts will lead to truncated DNA, truncated polypeptides, leading to truncated proteins. And proteins which are truncated will tend to get purified along with your normal protein. And so they can form, let us say, even if they're 1% of the protein and you're using it for some very useful or some very complex job, then the contamination is very, very dangerous. So quality control issues are also very important. So secondary structure as well as start site are important concepts in mRNA. That is it. I don't want to say anything else. Now we come to the translation problem, which is a far more serious issue. Now translational step. The translational step is very obvious. Let us start with the most obvious ones. What is the most important thing about translation? The most important thing is how does the translation take place? You're all aware there is a charged tRNA molecule which comes over.
Yes, sir.
So have you heard of this term called codon bias?
No.
Okay. So now remember that the mRNA is coming in and it is read as triplets, right? A, T, G, G, T, G, I. I'm sorry, I do not know what the codes are, right? I mean, and in X, 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 X. That is how they are read, right? Starting with ATG, and so on and so forth. And each of these represents an amino acid. You're all familiar with AA1, AA2, AA3, right? And this is how the polypeptide. Yeah, this is something which all of you know. Now, how does this do it? How is it done? For each ATG which enters this huge complex, the rRNA complex, ribosomal RNA, and the mRNA train is coming here, and each mRNA after it stops here, the rRNA brings here a tRNA. Actually a charged tRNA, because without the charge it will not be able to attach and it then gets discharged, as it were. And this tRNA has some funny structure, stem loop structure, that I will talk about. Something like this, I do not know. And here is the amino acid of interest, AA1. So AA1, and this here is called the anticodon loop. You're familiar with these words? This is all simple stuff,
Yes.
right? This is all well known. And this anticodon matches with this here. This anticodon here matches with this here in the, and therefore attaches AA1. So AA1 is attached because this is what it reads, and the tRNA comes and binds here. Now, the point that is to be understood is that each amino acid AA1 can be coded for by XXX, but also XXY, also XXZ. Sometimes the third base of, and so on and so forth. As a matter of fact, leucine has six possible codes. Even the second base, six possible codes. Some have two, some have three. So because there are 64 possibilities of arranging XXX, ATCG, and there are only 20 amino acids, and one of them is, out of those 64 possibilities, one is used up for stop codon. The remaining 63 can code for 20 amino acids. So 63 codons coding for 20 amino acids. By definition, there are 63 tRNAs available. There are 63 tRNAs available, and each of these code for 20 amino acids. I mean, so 3 of these code for one amino acid, 2 of these code for one amino acid, only one codes for an amino acid. So amino acids have multiple tRNAs coding for them. So notice that I could have AA1 being coded for AA2 being coded for, or AA3 being coded for by XXX or XXY or XXZ. Now all 3 tRNAs exist. All 3 tRNAs exist, and whatever code you present to me, if you present to me AXXX, then the XXX tRNA will come running here and attach the amino acid AA3. But if you have XXY, another tRNA will come running here. It will contain XXY, but it will attach the same amino acid AA3. So you can, the DNA, the mRNA can carry XXX, XXY, XXZ, but the same amino acid will attach, but different tRNAs will come and provide the solution. Now the problem with E. coli and the problem with all strains is that the relative population of a tRNA carrying AA3, amino acid 3, with XXX, and AA3 with XXY are not equal. This tRNA population is biased in each system, in each host. For example, XXX carrying AA3 tRNA might be 80%, and XXY may be 20% in E. coli. But in mammalian, this could be 30% and this could be 70%. Okay, so the tRNA, relative population of tRNA with different anticodon loops, recognizing different sequences but carrying the same cognate amino acid is different. So the population, there is a population bias, and hence this is called the codon bias. The codon bias is nothing but the population bias of the tRNAs present which carry the same amino acid but different anticodons. Do you all follow this argument? Is this clear?
Yes, sir, it is clear, but the number of tRNAs are not 63, but it is actually 31 only.
ये कहां से भैया, मैंने तो 31 ही होता है, ये किसने बताया आपको? विकिपीडिया में देख रहे हैं आप? भाई ऑब्वियसली उनको गूगल और विकिपीडिया को तो मानना पड़ेगा, वो भगवान है, लेकिन जहां तक मुझे पता है कि नंबर ऑफ टीआरएनएस आर लार्जर देन 31, तो उससे ज्यादा है, मतलब 20 से काफी ज्यादा है। ल्यूसीन से ही, ल्यूसीन में ही 6 हैं पॉसिबल टीआरएनएस। हो सकता है कि आप कोई पर्टिकुलर स्ट्रेन का देख रहे हो,
मे बी सर।
हाँ, तो मैं ये कह रहा हूं कि 20 एमिनो एसिड हैं और 63 है कि 62 है मुझे पता नहीं, बट मोस्ट प्रोबेबली 63 टीआरएनएस हैं जो कि इस 20 एमिनो एसिड को कोड कर सकते हैं। इसलिए कई सारे, देयर आर अ लार्ज नंबर ऑफ पॉसिबिलिटीज वेयर द सेम एमिनो एसिड इज कोडेड फॉर बाय मल्टीपल टीआरएनएस, एंड द बेसिक आर्गुमेंट दैट आई मे बी नॉट 63, मे बी 62, 61, पता नहीं, मुझे याद नहीं, ज्यादा स्टॉप कोडॉन्स के लिए हैं, है ना, 31 की जगह हो सकता है 61 हो, एंड दिस multiple tRNAs have different populations. So AA2, a protein AA3 may have 80% of one type of tRNA and 20% of the other type of tRNA in E. coli, but in the mammalian cell it will have 30% of one type of tRNA and 70% of the other tRNA. Now why is that? And that is a very interesting evolutionary question. So there is a codon bias. So when, and now this is the point that I'm trying to make, which is interesting. When you are coding for a protein, the cell knows. What does it know? It knows which proteins have to be abundant, which proteins have to be overexpressed or abundant because it needs them in much more quantity, overexpressed abundant proteins, and which proteins are required in very small quantities. Which proteins are abundant have to be overexpressed, and proteins which are produced in very small quantities. And what it does is that when proteins, those proteins which have to be abundant and therefore coded very efficiently, these proteins almost invariably carry the XXX code, which matches with the XX code of the more abundant tRNA. While small proteins, can you hear me? Let me hold on.
Sir.
Yes, sir.
So now small proteins which are small, can be coded for by the XXY code as well. Not small proteins, sorry, small quantities. I mean proteins which are rare, low abundance proteins, can be coded for by XXY. But proteins which are overexpressed abundant will almost invariably be coded for by XXX. Why is that? Because when this mRNA train is running in the ribosome and getting translated, it wants to make sure that XXX ka cognate tRNA available hai. Now, if you put XXY here, suddenly this is coming very fast. Their speed. At the same speed, the XXY carrying amino acid, because it is present in less population percentage, may not arrive here on time. And this will slow it down, or processing will slow down or stop. So this is called codon bias. if you have introduced XXY instead of XXX. Now you have introduced codons whose tRNAs for that particular amino acid are rare or are not present in the same abundance in the cell. This happens why? Because you have picked up a clone from a mammalian cell. You have picked up the gene from a mammalian cell. You pick up the gene from a mammalian cell. That gene from the mammalian cell may be overexpressed in mammalian cells, but there it uses XXY as the preferred codon. But the E. coli uses XXX as the preferred codon. So this is codon bias. So what is the preferred codon? And the word preferred codon is related to the percentage population of tRNAs carrying the anticodon, the required anticodon, cognate anticodon in the loop. Are you getting this argument? So this is called codon bias. Have you understood this?
Yes, sir.
Okay. Now, so what do we do? So therefore, there are all kinds of solutions. Now, this, if you have a heavily codon biased clone, then now earlier we had all kinds of very issues, but nowadays people say to hell with it, they simply synthesize ATG, and if you say XXX, so XXY laga do waise. Because nowadays it is very easy to synthesize genes. Earlier days, people used to sort of get very worried because they could not modify individual genes. Gene synthesis was an expensive business. Nowadays, you simply remove codon bias very simply by changing the third base. Earlier, we used to do more complex things like making copies of tRNA and cloning them inside. Copies of tRNA which code for XXX because you have put XXX. Because your cell contains XXY tRNA much more, therefore you clone for copies of tRNA containing XXX. And such strains are available. They are, Rosetta strains and all that, molecular biologists will tell you various kinds of names. Basically, they take care of codon bias by actually containing copies of some of them, or rather the critical amino acids. The critical amino acids which are most prone to codon bias, are, the mammalian equivalent of that amino acid tRNA. You get the point? The tRNA and tRNAs, the mammalian tRNAs, that is cloned and introduced inside the E. coli. So there are, RIL strains. RIL means arginine, isoleucine, and leucine के mammalian codes के tRNA introduced किए गए हैं. So you will see RIL strain or RP strain, where P is for, proline and R is for arginine, I is for isoleucine. So all these strains which are called RP and RIL are not rest in peace, but actually the cognate tRNA for the mammalian is also been introduced. So even if you have a codon biased gene, your gene is codon biased, you don't have to correct it. Nowadays people tend to correct it rather than use RIL strains. It's very interesting. How do you find out codon bias? How do you know whether you have codon bias? And it turns out that there is a very strong correlation. As I said, there is a very strong correlation, and all these studies have been done very, very seriously between, as I just now pointed out, genes which are overexpressed and genes which are poorly expressed. Genes which are overexpressed, proteins which are overproduced, genes which are overexpressed, almost invariably have a codon preference for high available tRNA. See the point that so first let me go back a bit. Now, measuring these tRNA levels is a tricky business and not very accurate. Measuring levels of tRNA, different levels of tRNA, is tricky. Nowadays people have done it, but I don't know how accurate it is, and I'm not very aware of the latest developments in molecular biology. But measuring this is difficult. So one of the ways is that people have looked at genes which are overexpressed. That is easy because you can take a cell, isolate the proteins inside, and find out those proteins which are most abundant. So for example, you can run an LC mass LCMS machine, take the cell lysate, and you can identify the 100 or so proteins which are most abundant. And when you find the most abundant proteins, then these proteins, you can go back to the genes, most abundant proteins, and you can go back to the genes and see what is the frequency. And so what originally people did was they did a very simple task thing. They picked up, I think 24 or 25 most abundant proteins. Those days, that is what they could do. And this was in 1987, I think. 25, nowadays people have picked up 50, but in the beginning they picked up 24 proteins, which were most abundant. And then they looked at, and of course these proteins were, each of these proteins contained all the 20 amino acids in multiple repeats, right? Because each were large proteins. So each then amino acid, AA1 to AA20, was checked, and they did what codon is used how many times. Is XXX used in these most abundant proteins? Is XXX used 80% times? Is XXY used 15% times? If XXZ used 5% times? And they made a list of all the 20 amino acids and what is the cognate tRNA from the DNA sequence, from the gene sequence. They could find out when was X, how many times is there XXX, how many times is XXY, and how many times is XXZ. And that defined the codon bias for each of these 20 amino acids. Each of these 20 amino acids, you define the bias. And then when you clone a gene, then each of your genes has a particular code for every amino acid, alpha, beta. Can you hear me? Alpha, beta, gamma?
Yes, sir.
Instead of alpha, beta, delta. So now you know how many times alpha, beta, gamma come here and how many times alpha, beta, delta come here. And so you can take any protein or any gene coding for a particular protein, divide it up into triplets, and find out that what is the times, number of times XXY is used, what is the time alpha, beta, gamma is used, and what is their percentage usage. So each amino acid can be assigned a particular codon adaptation value or codon adaptation, which is simply codon adaptation, which is nothing but equal to the frequency of the usage, the actual, let us say alpha, beta, delta is what you have cloned in. So frequency of alpha, beta, delta divided by frequency of alpha, beta, gamma, where alpha, beta, gamma is the maximum frequency, F max. F max is 80% here. For example, XXY upon XXX is nothing but 15 upon 80. While XXZ upon XXX is 5 upon 80. And of course, XXX upon XXX is 80 upon 80. So you can see that each amino acid can be assigned a value of codon adaptation, which is given by either 1 or 15 by 80, which is whatever it is. I mean 0.2 or whatever, or this is 0.02 or whatever. 0.1, I don't know. Sorry, I'm not doing the arithmetic here. So it is either 1 or 15 by 80 or 5 by 80. So each amino acid that is used in the gene can have a codon adaptation value, and this allows you very quickly to take and then actually define the codon adaptation index, CAI, for the whole gene, which is nothing but the geometric mean of all the adapted values. Which is nothing but, so CAI is nothing but Fi upon F max pi, this is multiplication, right? I equal to 1 to n raised to the power of 1 by n. Okay, this is geometric mean. This is the CI index, the codon adaptation index for every gene. Can you hear me? Hello?
Yes.
Yes, sir.
Yeah. So you can see that Fi by Fmax would be either 1 or 0.5 or 0.3 and all this, and the geometric mean of 1 and 1 into 0.5 into 0.3, I mean, and so on and so forth, whatever, raised to the power of 1 by, if there are 100 amino acids, raised to 1 upon 100. And so if they're all 1, 1, 1, 1, 1, 1, they're all using the maximum usage, then your CI is equal to 1. And it turns out that genes which have CI values of 0.8 and above, 0.7 and above, पता नहीं, 0.85, बहुत लोग अलग अलग बातें करते हैं. I will say 0.8 and above actually have no problems of codon bias. Whenever you have CI values of 0.5 or lower or 0.3 or lower, then you end up in trouble and you have to correct for codon bias. So you should not bother if the CI value is 0.7 or 0.8, but you start bothering. So you should calculate CAI of your gene, whether you need to change XXX to XXY or not, whether this is required to be changed. Whether you need to change the gene or not is found out by your CAI value. So let us stop here, and next class we will try to wrap up. So this is one of the important components of gene design, so that your protein is made in large quantities. So if you need a protein in large quantities, which is what you want for the product to be, your CAI has to be 0.7, 0.8 and above. Now, biologists don't do it, they just talk of codon bias, but I thought as an engineer, you should have a slightly more mathematical and a slightly more quantitative estimate of codon adaptation. That is why I talked about frequencies of tRNA and so on and so forth. So one is trying to sort of introduce a quantitative measure rather than talk in general that this tRNA is not used by the cell or most used by the cell. This is how biologists talk in slightly qualitative terms. You need to talk in terms of quantitative measures. Any questions?
Sir,
Yes,
could we
sir.
get a
I
question
have a
on?
question.
Okay, I'm sorry.
Sorry, one at a time, please.
So I was
Okay,
asking if we could get a question on CAI in the next class, calculating it in the next class if it's possible.
अच्छा बिल्कुल हाँ मैं I am a very disorganized guy, and first of all books and the book, as a matter of fact Monday you have a lab practical, and as usual I have not been able to shift you to Moodle, but please join the teams and let us see how many things we can put on the teams. All of you are on teams BBL 433P, that
Yes,
all
sir,
of you have
now we
joined?
are.
Okay, so
now
all
we
of you
are,
are in
yes, sir.
BBL 4, yeah, but Moodle अभी भी मैं sort out नहीं कर पाया हूँ. My abilities to handle computers is like zero. मतलब मुझे Word आता है और email आता है, इसके आगे कुछ नहीं आता है ना? So
But
you know
some
I'm a
of us
very
are-
sorry.
Some of us are still not on Teams. Like we have sent the request, but like we haven't been added yet.
Please send. No, but I yesterday only I sort of did all of them. Yes. Just one person was not coming.
I tried sending it again, but like it's not allowing me to send the request again.
Okay, if in each case you have sent me an email, right? Send me the email
So
again, and I will add you. I will add you individually. Yeah, or I will send you a meeting link. Okay, and then I will be added. You'll be added. Okay. Okay. So, any more questions on the class, on the course content?
Not about course content, but like I wanted to know like when did we start adding promoters of other organisms to microbes in which we want to produce proteins, and like I think that this is not very old technology, and if it is not like are these things industrially being used, and all these things are if being used, like how old this is? Yes.
This recombinant DNA technology started in the 70s. You know that mid 80s was the first successful insulin production by Eli Lilly,
Yes,
and
sir.
after
Yes, sir.
85
I
or
know
so,
about that. Really.
the thing has sort of has gone. I mean, crazy. I mean, today recombinant protein production is about a $50 billion market. So it's not a small amount of money. There are some proteins, especially in mammalian systems, which individually can be sold for $1 billion, $2 billion, $3 billion annually. And there are many proteins which sell for literally hundreds or tens of millions. And if you ever want to set up a technology, that is the way. Never try the billion market. Always try proteins which are sold in $100,000, because then you don't have competition. If you can sell 10 proteins of $100,000, $1 million, I think, is a good enough amount of money to carry in your pocket every year. So people in this country have this foolish notion of doing technology कि नहीं $1 billion वाला बनाएंगे. I call it the 1% fallacy कि हम Colgate बनाएंगे, Colgate toothpaste का 1% market पकड़ लेंगे. 1% fallacy. Colgate का market 20 करोड़ है, मैं उसका 20 करोड़ का 1% 20 लाख पकड़ लूंगा. भाई क्यों पकड़ने देगा आपको वो 1%? वो बेवकूफ तो नहीं है. He will not allow you to nibble into his market. So never compete with large players, because they will eat you up. So, but recombinant protein market is sufficiently diverse and large, so they can always pick up small proteins which nobody wants to produce because it is only for $100,000. The companies with deep pockets laugh at such amounts, and you pick up 10 such proteins and you are home laughing. Of course, you will not become you'll not become one of those Omicron or unicorns or whatever, but you will have a very, very comfortable life of producing 10, 20 proteins of $100,000, $200,000 each. Yeah, sorry, you were asking something that is different. I said went into technology. Go ahead.
No, sir.
So this technology is comparatively new. Yeah. Now the second point that I'm trying to make is that you made a wrong statement when you said that promoters from other systems are taking it. Almost invariably, other than T7, which is a viral promoter, most of the promoters that have been used are actually from the bacteria itself. And also, let me also tell you, synthetic promoters. Synthetic promoters where sequences have been redesigned and found by trial and error to be working more efficiently than the normal original promoter. Most of the promoters that are used in microbes or in mammalian cells, wherever they are used, actually belong to the cell. We have not reached the level of scientific understanding or perfection where we can design promoters to work better than natural promoters of the same bacteria. उतनी काबिलियत अभी हमारी नहीं आई है. आप लोग जब तक हमारी उम्र के पहुंच जाएंगे, हो सकता है वो काबिलियत आ जाए, है ना? But right now, our levels of understanding of biology in terms of quantitative analysis, engineering, modification. See, engineering is about design. Biologists describe. They just understand, they analyze. But we create, we design. And we think we understand the system only when we can change the system, when we can create the system. So in that sense, an engineering understanding of biology is completely lacking. Biologists can explain the system, analyze the system. Yeah, of course. But as an engineer, we don't understand even a bacteria because we cannot change it the way we want it. Engineers believe that we understand a system when we can design it. Okay, when we can change it, when we can create it, modify it. Biologists tend to say, haan, samajh mein aa gaya. This is how it works. So from an engineering perspective, we know nothing about biology. We are very, 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 very low end because ability to manipulate is still very low. Yeah, go ahead. Sorry.
No, sir. Thank you, sir. Now we have another class. Thank you, sir.
Thank you. Yeah, sorry. I'm sorry. We are getting into the other class. Yeah, I should not. Right. Thank you. Bye.